Hey everyone, welcome back to our first edition of the LlamaIndex webinar series in 2024, and we're excited to kick it off with LLMCompiler, which is a cool new paper that does parallel function calling for LLM agents. And so it's a cool new architecture for agents that optimizes both the system side as well as the performance side of things. So excited to have both Sehoon as well as Amir here from Berkeley, some of the co-authors of the paper. And without further ado, passing it over to you to take it away.
Thank you so much, Jerry. Thanks everyone for joining. Good morning and good afternoon, depending on where you are. Today, we're very excited to share with you our work on LLMCompiler, which is really a first attempt to create a compiler for, using agents, basically. And this is a joint work with Sehoon, who's joining me today. Sehoon Moon, he's the other first author of the paper. He's a fifth-year PhD student at Berkeley. Ryan Tabrizi, he's a third-year undergrad working with us, contributed significantly to the work. Nicholas Lee, he's also a first-year PhD student, as well as Michael Mahoney and Kurt Koitzer. So let's get started. So I wanted to very briefly talk a little bit about how we got here into this function calling. It was just a year ago, although it feels a very long time ago, where we saw this emergent behavior in neural networks. And it was very surprising that, for example, we had behaviors like in-context learning, where you would basically provide the model with a couple of examples of, what the input-output looks like. So for example, here is like translation from English to French. And then without any other instruction, you would basically ask the model, what is the translation of cheese, right? And then we found that after a certain size, these behaviors exhibit, which is very, very surprising. Actually, this was not how few-shot learning worked before. And then people started to play with this. People were like, okay, what if we actually start adding more instructions rather than just input-output? What if we start adding instructions and see if we can actually solve important challenges such as math? So LLMs have been known to struggle with math. So people found a very interesting way to solve this by using this few-shot learning type idea or in-context example idea. And so one of the famous ones is chain of thought prompting, where the idea here was when you're providing the examples in your prompt, tell the model how you arrived at the solution. So here, instead of just saying that for this question, the answer is 11, what if you actually provide the reasoning? And the LLM could then mimic this behavior and arrive at the right answer. But still, there are cases where this is not possible. So for example, if you have complex math, especially large numbers or math that's non-trivial, then LLMs still fail, even if you do this kind of prompting. The other thing is that LLMs have a cutoff knowledge, right? So for example, if you have a database that you want to query something that's like a private database, let's say you're using LlamaIndex, then you do need to query that data and provide it to the LLM. And the LLM has a knowledge cutoff that either doesn't have that public data, or if it's private, it didn't have access to that. So then people thought, is there a way that we could provide tools for the LLM to use to basically get this data, or tools to use like a calculator, like what we do, right? We don't know all of the, complex arithmetic. When we want to do complex arithmetic, we use calculators. And so this idea was made possible by a very, very interesting solution. So this is the Toolformer paper where they came up with a very interesting solution. So the idea was the following. We tell the LLM that you have access to the certain tools like calculator, like for example, a database query, like, imagine it could be any kind of tool. And then we ask the LLM, every time you think you need to use this tool, just output some special tokens, and I will help you afterwards. So for example, here, when the LLM is basically producing the outputs, we ask the LLM, if you wanted to use the tool, basically start with this open bracket, the tool name. So here the tool name is calculator, and then the arguments that you want the calculator to work on. And then we will stop the execution ourselves. We would call this tool, we get the results, and then we provide the tool for the LLM. So this kind of intervention allows us to use tools. And this really unlocks a lot of really, really interesting work. And so to just show you this, just wanted to show you this plot that by using the tool, you're able to significantly improve the performance on math problems. And then this has been really, started a lot of interesting applications of different tools, function calling, API calling, etc. Right? So for example, how OpenAI does this is when you get to this point, instead of starting with this kind of special characters of, open close brackets, they output a JSON. Stop the execution, output a JSON, and say, LLM requires you to call these APIs or these tools. You call them, and then you continue the execution. And so on top of this, one of the questions was, what is the best way to do this, right? We can basically start here and say, I'm going to start with open close brackets, then I'm going to give the solution like this. But is this the best way to do the function calling? Is that how we actually use function calling, right? Probably not. So in our brain, when you're, for example, doing a very complex, mathematics, you're like, hey, wait, I can't do this in my head. Let me use a calculator. So this was kind of the high level idea of React, where they said, when you want to use React for function calling, when you want to use function calling, what if you actually ask the LLM to first reason why it needs to use a tool? We call the tool, and then we provide the LLM with the observation. So here is an example, actually a typo. So let's say we ask the LLM, this is from Hotbot QA, where Scott Derrickson and Ed Wood of the same nationality. And so maybe you don't know this, right? What do? We say, okay, I don't know it. I'm going to use Wikipedia or Google to figure out their nationality, and then I'm going to answer the question. That's basically the framework of React. So the LLM starts and says, I need to search Scott Derrickson. It calls this search tool with the argument Scott Derrickson. It gets the data here from Wikipedia. Notice this American filmmaker is in the bio. And then it's like, okay, now I know where Scott Derrickson is from, but I still need to do another search. I need to search Ed Wood, performs the search, and then comes up with the, we give it the observation like this. And here, there's also an American filmmaker. And then LLM looks at all of this data and is like, okay, now I have all the context I need. Let me answer the question. And of course, the answer is yes. But there's a lot of problems with this approach. And one of them, this is an exemplary case, is that the LLM could get into an infinite loop. So React could get into an infinite loop. So for example, if it calls this tool like search John Smith, there's many John Smiths, right? And if your function call returns something like, hey, there are multiple matches for John Smith, it could refer to this, could refer to that, could refer to that. It may not recover from that. It may continuously keep calling search for John Smith. Another problem is that if you notice, even here, when we are doing this kind of thought and action, we are doing it sequentially. So we are calling this function, getting the result, asking the LLM, okay, I have these results. What else should I do? Then you perform that step. Then again, you provide all of that context and you keep calling it. And so this context keeps basically growing. And this is problematic because of context length limit, but also latency and accuracy. And one of the reasons that accuracy is a problem is because these intermediate observations could contain data that could actually mislead the LLM. So another common failure with React is that it could actually stop execution. It makes an observation and it forgets that it needs to make a couple of other function calls because of these intermediate representations. So people have proposed a lot of interesting solutions. Author of React, for example, has proposed interesting solutions for this that could resolve some of these problems. But if you take a step back, there are problems that seem like we need another tool to solve them. So we talked about accuracy, we talked about sequential execution, but there's questions around reliability. Intermediate results can affect the LLM's ability to even continue the task, or it could incorrectly answer the question. There's question around testability. Like if I'm developing a very large scale, imagine maybe next year, a couple of years from now, we have thousands of APIs and we have large scale intelligent software. How can we write unit tests for this, right? We can't just have complete integration testing cover everything. It's actually very difficult to do that. LLMs are very incapable of doing long-term planning. So if you have a task that requires calling many different APIs back to back, because of this sequential execution and the fact that we're not following a plan, it may diverge. It's very difficult to do debugging. Like what's the equivalent of like a PDB? What's the equivalent of knowing that, okay, the LLM failed, what happened? What we should do right now is basically go and look at all of those thoughts and actions actually manually and kind of think, why did the LLM make the mistake? Maybe that's okay for the example I showed, but imagine if you have a very large scale software, that's not possible. But there is a good thing. The good thing is that LLMs are very good at simple cases. So when you only want to make one function call or maybe two function calls involving like simple calls, they're very good at that. So can we actually use that? Well, let's take a step back. When we are writing code ourselves, like the very first thing that students are taught is that what is a good code? A good code is a code that is comprised of smaller pieces, what's known as like the factory method. So you basically write your code into smaller pieces that are easy to reason about, it's easy to debug them, and it's easy to write a unit test for them. And then we write a control logic, which calls many of these functions, right? That's how we write good code. So can we do the same thing for LLMs, right? So if we take this operating system view from Andrej Karpathy, what is the equivalent of writing good code for this intelligent software? Well, if we had a way of orchestrating the calls to the LLM, so basically you're like, I need to use a calculator here, I need to use Wikipedia search here, I need to call, basically load something from this database, then if you're able to orchestrate it and every time tell the LLM, this is what I want to achieve, and this is basically the context, then you can provide a lot of the, you can solve some of those problems. And you basically need a compiler and operating system for this. So the idea is that you have your language written in English, you have a compiler that compiles this into smaller components, and then ask the LLM or the CPU, for example, here to execute each one of those smaller pieces. It's kind of similar to how our CPUs today do addition and multiplication, right? And bit manipulation. That's basically when we're writing program. CPU doesn't do matrix multiplication. CPU does addition and multiplication, and matrix multiplication is created on top of these instructions. So what's the equivalent, equivalent case for LLMs is the question we're trying to answer. And there's a lot of interesting possibilities here. So for example, one of the cases that we're considering here is that this compiler or operating system could even route the task or the function call to the correct LLM depending on the complexity. You can have multiple LLMs, of different capabilities, GPT-4, GPT-3, or different Llama, and then the compiler can decide which one to route to, or maybe all of them at the same time to speed it up. So to talk more about the very first MVP that we've come up with, I'll pass it to Sehoon to present our first attempt at solving this problem. Sehoon?
All right. Yeah, I will. Okay. So let me go into more details. So thanks, Amir, for motivating us to why we need the compiler for LLM usage. So we really need a compiler for LLM function callings for different reasons that Amir has talked about. And well, the role of compiler in this case is to efficiently and effectively orchestrate various function calls within the LLM usage and then handle correctly their dependencies. So we were the initial attempts to bring this compiler concept to the LLM agentic systems. And let's maybe take a look at the example that we had before, which we took it from the HAPA QA benchmark to compare the Scott Derrickson's nationality with that of Ed Woods. So if we can consider how React would behave, it will basically launch two separate search tools to search for the nationality of these two people, which will eventually happen in sequential fashion. And at the end of those executions, your LLM will have enough knowledge to give us the answer. But if you look at this example, it's pretty evident that those two search tools are independent from each other, and therefore we can run this in parallel. So that's how we came up with the LLMCompiler solution, where you had a planner which can decide ahead of time that these two search tools can be happening in parallel, and then let it execute it in parallel, and let it not interfere to each other. So there are multiple benefits that we can have from having this scheme. Obviously, you can reduce the latency because those search tools do not have to wait for each other's execution. But also in terms of cost, we will save a lot of cost because we will save unnecessary LLM calls for individual reason and action step that is required within the React framework. And also in terms of accuracy, right? These search tools will not impact each other's, and their outputs will not interfere with each other's. So this can potentially lead us to, more correct behavior and then better accuracy potentially. So going more into the system design of LLM compiler, this is the system diagram, which has 3 different components: LLM planner, task fetching unit, and the executor. And LLM planner is the essential part within our LLM compiler, and it faces the user input directly, and it uses the sophisticated reasoning capability of large language models to be able to understand the user input and then decompose it into multiple actionable tasks along with their arguments and then their dependency patterns. So here in this case, when user had asked about what is the ratio between Microsoft's market cap and then Apple's market cap, your planner will be able to decompose this into 2 different search tools to search for the market cap of these 2 different companies, and then subsequent mathematical operations so that we can get the ratio out of the market cap results that we got back from the search tool. And then potentially LLM that can maybe summarize the overall results and get back to the user. Because we don't know the results of the search operation before we get it to execute, we don't know the exact argument that goes into the maths. So that's how we brought this placeholder variable, which will be eventually filled out once the associated prior tasks are done. So this placeholder variable will define the input and output relation between different tasks, and this will eventually define the dependency pattern and execution graph. And once the plans are planned out from the planner, they will all go to the task fetching unit. And if there are those of you who are familiar with the computer architecture, this is more or less similar to the modern computer architecture, the instruction fetching mechanism. So it's sort of like a queue. It stacks up all the tasks or the plans that has been generated from the planner up until the point that all the dependencies are resolved. So if you can think about the third operation, which is the maths operation that depends on the first search and then the second search, upon their completion, we get the results, feed it back from the executor to the task fetching unit, get all the placeholder variables to replace with the actual values, and then that's the moment that we can actually get this fetched into the executor for its execution. The final component in our system is the executor, and it's equipped with a bunch of tools the user may have provided, and then it delegates the task that has been fetched from the task fetching unit to the associated tool and let it execute it. Tools in this case can be simple functions like calculator or Wikipedia search, but it can be as complicated as some dedicated LLM agents that are designed specifically for very particular use cases or very particular tasks. So all these things like planning, task fetching unit, and executing, they are all hidden from the user, which is a cool thing about LLM compiler. And this will all handle automatically given the user input. So from the user point of view, what needs to be provided is pretty simple. We first need to provide the tool definition, which is same as how you're engaging with other frameworks like React or even OpenAI's function calling. And it's essentially like describing your tools, the name of the tools, what are the arguments, what are the types, and what are the expected outputs. So more or less the same as how you're engaging with the other frameworks. Also, additionally, the user can provide in-context example for the planner, because all the performance or end-to-end accuracy relies on the planner's capability of correctly identifying the tests and getting it into executable graph. You may want to provide some in-context example on some of the expected inputs from the runtime and how they are decomposed into a execution graph in a semantically and synthetically the correct way. So those are the system components and how user can configure our framework. And let me get into the evaluation of our framework. And before we do so, I would like to illustrate some of the examples that our framework or the user may give to our framework, and then how LLM compiler is expected to decompose it into dependency graph. So on the far left, we're seeing the simplest case. For instance, when you are comparing the sales data of Apple or Microsoft, this is not so much complicated than just launching two different jobs in this case in parallel. But you can also expect more complicated use cases where the task has to be decomposed in a way that it involves multiple different tools and different inputs and output relationships that are all intermingled together. So those are illustrated in the second and then the third examples. And our evaluation really focused on, well, is your LLM compiler is capable of decomposing those of the tasks into the correct dependency graph and then get the final output as what's been expected. So coming up with the simplest case where you have a bunch of tasks that can be all launched in parallel, so to say, inversely parallelizable function calling patterns. To evaluate our framework in the simplest case, we have chosen two different benchmarks from what's available in public. So one is HAPA-QA, especially their comparison data set. Just like the example that we have seen earlier in the slides, where you have to compare the nationality of these two people. This HAPA-QA compares a bunch of more examples that has two-way parallelizable pattern. And this can be easily solved by your LLM by equipping it with Wikipedia search tool. Another interesting benchmark that we can use from the public is the movie recommendation from the Big Bench suit. And just like what you see in this example below, you are given 4 different movies as an input, and then another set of 4 different movies as an option. And then out of those 4 movies in an option, you basically need to choose one movie that is the most similar to the 4 movies that are given above. So this defines 8-way parallelizable workloads, and your LLM needs to search for all those 8 different movies to be able to be fully informed about them and then make the best decision. So this is the table that we have comparison of our methods against some of the benchmark, some of the baseline methods that we chose. First of all, we are comparing against the sequential execution-based React methods. There's one React without dagger. There's another one with dagger. The one without dagger is the plain React, but the plain React, we have observed a lot of failure cases related to, as mentioned earlier in the slides, some of like repetitive function calls that falls into the infinite loops that you search for the same entities over and over, you would never get out of this loop. Another failure cases is early stopping. So for instance, if you had to search 8 different movies to make the best decision, React would end up searching for maybe 4 or 5 different movies. It decides to end up the execution because it knows it has enough information to make, the decision, which is in a lot of cases premature decision, and that's unexpected behavior. So we were able to prompt React in a way that we can avoid the situations as much as possible, and that's the React with the dagger. So another benchmark that we have chosen is OpenAI's parallel function calling, which has been announced in the OpenAI Staff Day, and it was like a couple of weeks before we published our paper. So those are the baselines that we have compared our methods. We applied LLMCompiler in conjunction with GPT as a closed source model, but we also use it with Llama 2 70 billion as an open source model. And this demonstrates one of the benefits of LLMCompiler, that it can also be used with open source models like your custom models that has been trained on your custom data, which is not available for OpenAI's parallel function calling feature, which is bounded to their own ecosystem of GPTs. So looking at the speed up, latency speed up, those speed up number is relative speed up number with respect to React. And then we're seeing 1.8x speed up to 3.7x speed up on these two benchmarks, because we can launch the execution in parallel, and we can save a lot of unnecessary back and forth for every single reasoning and action step. Here we are also observing some interesting speed up of up to 30%, even when you're comparing this with OpenAI's parallel function calling. There's not much we can reason about this because all the behaviors of OpenAI's parallel function calling is hidden from the user. Our speculation is that there might be some overheads related to, validating the inputs, validating the functions, combining them all together and providing as a context. But those are our speculation. Also, when you look at the accuracy, we're seeing when you compare the plain React to our method, we are seeing a constant improvement of accuracy. And we expected that, we hypothesized that this was because of failure cases that we mentioned, like repetitive function calls and all these stoppings. So this can be handled by adding additional prompts for React, but still, this is not 100% solution. So we are seeing, on par or even better accuracy, even comparing to the optimized React. And also compared with parallel function calling, LLMCompiler can also have on par accuracy. So also in cost wisely, LLMCompiler can have up to 3x or 6x cost reduction on each of those benchmarks, because it will avoid unnecessary LLM calls for every single reason and action step. So that's how we evaluated on the most simple case. We have additional evaluation in our method for more complicated tasks that involve like different dependency patterns. But in the interest of time, we skip this part, but it's all available in our paper, which we have the same observation as what we had for the simplest case. But here in this talk, I would like to spare last couple of slides in discussing the replanning capability. So LLMCompiler needs a replanning capability. This is not just for LLMCompiler, but it's more general statements to all the LLM-based agentic solutions, because your initial plan might not always be perfect, right? There are lots of failure cases. One of the cases would be, in various applications, your execution graph can only be constructed based on execution results of the previous plan or the previous function calls, which is unknown a priori when you're planning out. So one common example would be when you're buying an item on the web, right? You can go to, say, Amazon webpage, you can search for the entity and you can click on the, search button, but you cannot plan out beyond that boundary because you don't know a priori which will be returned as a list of candidate items before you actually get it to click. The second case will be, your plans may fail or it's not be perfect because of some unexpected outputs that will happen on the fly. And this can never be anticipated in the planning phase. So one case will be search failure. Your search engine may return unexpected results. Your search will fail because of, temporal issues like, internet disconnections. And in this case, your plan needs to be changed. So that's how the replanning should be incorporated into the framework, so that your planner can only plan out the part of the entire plan, see the intermediate results, and then plan out the rest. Or your planner has to adjust the original plan based on how it fails during execution. So this can also be incorporated into LLMCompiler. Once all the initial plans are executed, you ask your LLM whether you can answer directly to the user. If it's answerable, it's good, right? It's the end of the execution. But in case where it goes wrong, we have to go and do a replanning, in which case you have a feedback loop to provide the LLM planner with additional context that, there are additional information we need, or this tool has unexpectedly failed for whatever reason. And based on that, your planner will come out with a second plan that goes to another loop of planning and executing. So here's a evaluation method that we have evaluated this replanning capability of LLMCompiler. We used the game of 24, which was introduced as one of benchmarks for tree of dot paper. It's a more of a logical task. You're given 4 different numbers, and you have to make 24 out of any combination and any conjunction with any type of mathematical operations. So here in this case, maybe you can subtract 4 from 7 and then multiply by 2 and 4 to be able to make 24. So how tree of dots solve this problem is it goes through a iterative process of dot proposal and then state evaluator. So given those 4 numbers, your dot proposal will pick up 2 numbers and then connect with math operation. And then it will come out with a bunch of proposal, maybe add 4 and 4 together, subtract 7 and 4 together, or divide them. And then after it proposes multiple candidate paths, your state evaluator will basically see those paths and see if those are promising or not. Maybe this is less promising, that is less promising, but this might be more promising, right? And then it moves on to the next iteration, where you go on to a next iteration of dot proposal and state evaluator. So here in this case, we see that there is a clear boundary where you cannot replan ahead. So because the dot proposal of the second step depends on what's been survived and what's been pruned out from the first step, you cannot replan beyond this boundary of step 1 and step 2. So that's how replanning can chime into this framework. So we compare LLMCompiler against tree of dots, and one limitations of tree of dots is that because all this dot proposal and state evaluator has to be executed all in a sequential way, it results in a significant latency overhead. But because our LLMCompiler can solve this problem by using the replanning capability, but at the same time, it handles all the parallel tasks for dot proposal and state evaluator properly, we can reduce the latency by up to 2x or 3x, depending on what models you're using. Yeah, so those are evaluations, and this is the entire table that we have included in our paper. We have tested our method in different test bench that has different dependency patterns, as well as some of the tests that will need replanning. And here we are seeing speed up, we're seeing cost reduction, and sometimes accuracy improvement. So hopefully this will inspire people on how we can design agentic system in a way that we can be more efficient in terms of latency and cost, as well as more performant in terms of error proneness or accuracy. And hopefully this will guide us to a better way of designing, more scalable solutions to build up more complicated agent system that are targeted for complicated tasks and various applications in various different, scenarios. And yeah, these are the references. And yeah, thank you for listening. And we have our paper and open source code base available, so feel free to test it out. And we were lucky that we have LlamaIndex integration, thanks to all the folks from LlamaIndex. So hopefully you guys can enjoy this. Thank you.
Thank you. Thanks, Sehoon and Amir. That was a great presentation, and we'll get to the questions in just a bit. I know, I think you've already responded to all the questions, but I figured we just read it out loud for kind of like the YouTube listeners as well. Maybe just before we get to that, in about the span of 2 minutes, I am going to show you kind of roughly where you can find the LLMCompiler implementation in LlamaIndex. So basically, you just go on Llama Hub. Llama Hub's just, for those of you who don't know, a source for a lot of different integrations, including data loaders, tools, Llama packs, and datasets. So this is actually implemented as a Llama pack, which is actually just a template you can download, modify, and use for your own purposes. So you just search for LLMCompiler, go here, and we basically implemented a version of LLMCompiler and borrowed, lifted a bunch of code from the LLMCompiler repo. So, a big shout out to the authors for kind of having a open source repo along with the paper, and we adapted it using LlamaIndex constructs. And basically, there's a notebook guide that you can find here as well that you can basically clone, download, use for your purposes. And what it actually shows is you can actually use LLMCompiler not only over like kind of simple calculator functions, but actually over like a RAG pipeline, which is kind of one of the core focus areas of LlamaIndex. And so actually, I have like a notebook example here. Given a bunch of Wikipedia pages around like different cities, this is a very toy data set, obviously, but given like 5 cities, you can say like you've indexed like the papers for or indexed the text for each of these cities. You can actually kind of initialize your LLMCompiler agent worker using with GPT-4, and then actually go down and ask a question like this, like tell me about demographics of like 2 different cities, just a very kind of toy question example. But if you look at the debug output, you can actually see LLMCompiler in action. So it generates a plan, right? It generates, okay, first I want to query the vector index for Miami, as well as the vector index for Chicago. And then I want to join the 2 together. And the thing is, like, if this was a React loop, like it might reason about this too, but one, it wouldn't actually do this long-term planning beforehand. So it would actually first be like, oh, like thought I need to go into Miami first, and then afterwards thought I need to go into Chicago. Here it actually just plans it out beforehand. And because these 2 are actually parallel, there's some algorithm in there that identifies dependencies between the graphs. Then it actually executes the 2 in parallel. So you can kind of see that here because they're executing out of order. But it looks at vector tool Chicago, vector tool Miami, thought, both of these are diverse cities, and answer you can look at kind of like the response from both of these. So I encourage you to try it out. I'm sure I might have kind of implemented it in some way where like there's things that break. And so please feel free to file a GitHub issue and let me know your feedback. But with that said, let's go to the questions. So I think this was already covered, Sehoon, but maybe just for clarity, one of the first questions is just what is the explicit difference between this and OpenAI parallel function calling?
So the question was comparing our methods to OpenAI parallel function calling, right?
Yeah, just what's the explicit difference? And I'm sure I could give a stat too, but we'd love to get your thoughts, like in terms of like the methodology.
Yeah, so OpenAI parallel function calling is you look at the input and you look at the current state, and it can only plan ahead a single step. So you can imagine like there are dependency graphs that has multiple depths, right? You execute this first and then use the output of this level to execute the second item that goes to the second depth and so on. If you can imagine certain dependency pattern, OpenAI parallel function calling can only, take one step after another. So maybe it's better that I can share a screen to give a more concrete example. Do you know how to? So looking at this example here, OpenAI parallel function calling can only find these 3 search tools can happen in parallel. It cannot plan beyond this boundary and plan out the math operations. So once the search tools are getting executed, we have to run OpenAI parallel function calling again with all the search results appended when it can finally output, this math tool can be happening, right? Versus in our scenario, we can have the entire graphs to be generated just by a single shot, and that results in less LLM calls, and then better planning strategy.
Sweet. The next question is one member from the audience asked, like, kind of basically the analogy between LLMCompiler and CPU architectures, and basically like how complex basically the LLM tool itself could actually be pretty complex, right? So in like an agentic architecture, like the tool itself isn't just like a simple arithmetic operation. It could be like a completely different agent that does a bunch of different things. And so kind of high level, maybe the question is, what are your thoughts on like the similarities and differences between like a CPU like based architecture as well as this like agentic architecture, especially going forward?
Oh, Amir, do you have a?
Sorry, yeah. What was the question? Sorry, I was answering the other chats.
Yeah, I see. It's basically going to the second question, which is, it seems like there's probably some differences between this and CPU architectures where like the tools themselves could actually be quite complex. Like if you imagine the tools could actually be other agents or other kind of things that actually execute multiple steps. And so curious to hear your thoughts on high level similarities and differences between like the CPU architecture, right? Traditional computer architecture with like this agentic architecture you're proposing.
Yeah, I think that's a great question. Actually, we were discussing this yesterday, about like in these other GPTs that, he's here. One way of looking at this could be, is to see this as like auxiliary units, like, like GPUs and CPUs, where you have the CPU and sometimes it offloads a set of, computations to the, to a particular dedicated unit like a GPU. That's one way to look at this. But yeah, that's right. So some of these tools actually could be routed back to the, like it could be a whole flow for itself, right? It could be a complete, like essentially like in our own like software programming, right? You can have like a recursive function, or you can have like a function that involves like 100 different, calls basically. Yeah, I think that's a good point. Maybe we can think about it from like this CPU, GPU type, auxiliary processor type view. Maybe we can look at it like function calling unit is also an interesting suggestion, and I think the person who asked the question suggested that.
I think another interface that could be interesting, analogy that could be interesting, is just like microservices. Like basically everything has like a defined API interface, and it's actually like a communication between different things, which generalizes beyond like one machine into like a multi-machine setting. The next question is kind of similar, actually. I think there's a lot of questions basically at a high level, kind of asking about like the similarities and differences between kind of like concepts from the CPU architecture you can bring over into like LLMCompiler and back and forth. So this one is kind of about like error tracking. It's not really a question, but like the flavor is basically, how can you basically kind of use this like DAG-based planning to do like better error tracking testing? I think you actually mentioned that at the beginning of the slides as well. And for instance, like Airflow has DAG-based error tracking, and curious like how many of these concepts you can bring over kind of given this current architecture.
Yeah, that's a great question. Actually, that's, one of the things that, we're doing in our programming, like in software 1.0 is like, we have, try except, right? We have a lot of, like when this happens, we know exactly what's the flow that we can take. So one of the benefits of, breaking this like software 2.0 or 3.0 type, paradigm into smaller pieces is that each of these smaller pieces, we can basically have more constrained logic around it. So let's just use the calculator example, right? If the LLM made a mistake and included some characters as the arguments of the calculator, well, I mean, we can write like code around that to basically capture that bug and actually autocorrect it, right? Tell the LLM for just that tool usage, you made this mistake and you need to fix this. And this is also part of what, when you're using, ChatGPT, like, it tells you, run this code, you run it, you get an error, and you're like, hey, I actually got this error. It looks at that and corrects it. You can consider that kind of a flow. This could be a possibility for making basically the model more constrained into the behaviors that it can do, and can actually be good for safety. It could be good for fault tolerance because you can basically constrain it. And it could be good for better reasoning about the flow of the execution. But we are going to look at the airflow, and we're going to see if that could be something that we could integrate into LLM compiler. The current version of LLM compiler, just to clarify, doesn't have this right now, but this is something that could be added.
Another extension on this, and I think this is brought up by a member of the audience, is this idea of like caching, which kind of gets into just like how do you cache like intermediate results, kind of similar to traditional like CPU architectures. What places do you think could potentially use like caching, memory, like some sort of fast lookup?
Do you want to take
Yeah. So in the current implementation, we say we have two different tools. One has to be executed, and then the results have to pass down to the second one, right? In the current implementation, we pass it directly to the second tool as an input argument, so that only the subsequent tests that require the output of a certain function gets the output, and it doesn't affect any other tool usages. But you can also imagine there might be some output knowledge that can be used across like different tests, right? So we can imagine we also incorporate some sort of like a notion of global memory where you can help out the entire plan. So this could actually be the thing when you have to do replanning, right? If you're doing replanning, you would like to know what tool fails and what was the reason, in which case you want to put down some of the output or failure cases to the global memory so that it can be, through the feedback loop, it can be forwarded back to the planner to make it plan out the next iteration of a plan, right? So to give you a short answer, we were only forwarding the output as an argument to the consumer tasks, but we can also have a dedicated global memory that can, help us manage the entire processes, including the replanning.
Sweet. Yeah, I think this covers a few of the questions that were after this as well. Maybe a fun question, like, do you know any kind of companies or people like using this in real world use cases?
You mean the LLMCompiler?
Yeah, or concepts similar to it. Yeah.
Mm-hmm. Oh, Amir, do you want to take a step at this?
Yeah. So there are a couple of people that we're talking with that are using this, especially like, for example, one use case is, around like, web agents, that could call different websites or explore different, like do different explorations in parallel. There are cases where you actually need to call multiple different databases. So for example, you have, imagine like, you have like a private case where you have multiple different databases, and depending on the query, you may need to basically, ping couple of these databases, right? And then you need to have some stochastic logic around that. We were talking to a company that's doing this for like a B2B case where the input, all the APIs are there, but they have many, many APIs. So you cannot put all of those APIs in the LLM tool definition. But this planner kind of helps you with, deciding which one to call and then basically orchestrating it. Or even like another use case, like if people are familiar with Perplexity, although they're not using LLM compiler, just to clarify this, one use case is that, you have multiple different engines that you can, like, once you get the query, you can call, and you can do all of these in parallel. Let me actually first look at Wikipedia. Let me look at this private database that I have. Let me look at Google results or Bing results, and then basically then join all the results and provide the solution for the user. Really, anything you can do with OpenAI function calling, and it requires multiple steps, could benefit from this framework.
Sweet. The next question is on the extensibility to non-OpenAI models. I think some people are interested, for instance, in using this on like Mistral or Claude or some of the other models coming out. And then I'm going to add the extra step because I think this is another question, like how do you potentially incorporate multimodal models into this? Curious to get your thoughts on both like extending this to open source models as well as multimodal models.
Yeah, I think there's nothing blocking us from extending this to any, open source models. We have generated the very generic framework that you can switch the backend model just by, it's just as easy as how you can use the other, LLM solutions using different backend models. So switching to different type of model architecture isn't a big deal in our framework. It's orthogonal direction, and switching it to the multimodal models. This is going to be a pretty interesting, directions, because in a lot of cases we expect the input to have multimodality. Our current implementation is not aware of the multimodal, but we do think it's a pretty useful applications. And once we find a good fit, we are now going to and willing to supply this.
Sweet. This next question was actually something I was thinking about too. Is it possible to kind of extend LLMCompiler with like the DAG-based planning with some aspect of human in the loop for each step, so that you can basically have like incorporate human feedback at like different stages of the plan, and how do you plan to incorporate that?
Yeah, I think this is very useful features to be able to solve more complicated problems, like say in the use of, say, web navigation, right? Web can fail in different cases, and it may end up like, it may have a pop-up window that has to be interactive with the user. Maybe user has to type in their own, password, IDs, and click on something by their own needs, in which case, LLM may not decide on its own, right? So maybe two ways that we can incorporate this is maybe like, first of all, we can have user interaction or like get a user feedback as a separate function that LLM can invoke, right? And if we know ahead of time from the planner that this part of the action needs an input from the user, it can use that tool to plan out that particular task, and then that will eventually let the executor get the user feedback and then move on to the next step. But also we can have alternative way of doing this, where you can incorporate this into the replanning loop, where like if certain thing fails because it doesn't have any user feedback, your replanning will basically ask the user to provide more information so that your LLM can be more informed in solving, and getting out of those issues, right? So I guess those are two solutions that we can have human in the loop for, this LLMCompiler process.
Great. And then I think we probably have time for like one or two more questions. And then I think one of these goes back to one of the topics that you've talked about, but basically like, can the compiler benefit from trap memory? And actually, I think there was another work a few months ago from like Joey's lab at Berkeley that was on MemGPT, which is also like computer architecture inspired with like kind of hierarchical memory. I'm curious if you have like extended thoughts on how do you like kind of think about how this like memory component could be brought into this overall idea of like an LLM operating system?
Right. So yeah, this can be pretty useful when we have to do long-term planning where like all the intermediate results has to be stacked in, say, global memory to guide us to multiple iterations of replanning, or like even within a single iteration of planning, right? In which case the context length might go and blow out. And in that case, we can design our memory to be more optimized in a way that it can put specific things depending on the context where you're at. And I guess that's how we can incorporate the smarter way of memory management in terms of like something similar to MemGPT or other extension of the work. So I would say it's pretty much orthogonal. Maybe we can have our planner to have a explicit control over it by defining some primitive tasks that can manage your memory, or you can have it hidden from the planner by letting it happen automatically.
Sweet. And then maybe just to wrap up the webinar with the last question, so this is great. Clearly, like, it's a step towards building this architecture. What's the next challenge that you're interested in solving, or like next kind of extension that you're interested in tackling?
Yeah, in my opinion, because we have built some compiler analogy, we brought the compiler concept of compiler from the classical methodologies to this like LLM field, right? So we can think about some optimization techniques that had been happened for the classical compiler, where like we can do some code optimization, right? So if you have like multiple agents that have their own LLMs, maybe some of the tasks may be easy enough so that we can use a smaller model. Maybe some of them can be, pretty difficult or task specific, so that we have to be pretty picky on like using a larger model or even, fine-tuned model. And it will be cool if your planner can, decide this ahead of time so that we can have dedicated engine that goes to specific tasks so that we can use the resources in a more optimized way, right? And this is pretty much similar to like how optimization would happen in the classical compiler. And something similar in that notion, we can bring up like a lot of concepts from the previous fields to this new field, right? And I think those are going to be opening up a bunch of different directions.
Awesome. Well, with that,
Yeah.
thank you so much, Amir and Sehoon, for your time and for also answering all the audience questions. It's a fantastic presentation. And for those of you who joined in late or who are listening, we'll have this recording up on YouTube. And if you have more questions, please feel free to leave it in the comments below. All right. Thank you.
Thanks.
Thank you.